Hello everyone, my name is Nur Alia binti Hazrin and today I will be presenting about my final year project titled Removal of Ibuprofen from Aqueous Solution using Biomass Derived from Rambutan Seeds. This project focuses on producing activated carbon from rambutan seeds and evaluating its potential as low-cost absorbent for removing ibuprofen from contaminated water. Ibuprofen is one of the most widely consumed non-steroidal anti-inflammatory drugs or NSAIDs. Due to its extensive use, traces of ibuprofen are frequently detected in rivers, lakes, and wastewater. Unfortunately, conventional wastewater treatment plants are not designed to completely remove pharmaceutical compounds, allowing these contaminants to enter the aquatic environment. Long-term exposure may negatively affect aquatic organisms and potentially pose risk to human health through water reuse. To address this issue, this study explores the use of rambutan seeds as a precursor for activated carbon. Rambutan seeds are an abundant agriculture waste in Malaysia. Since they contain high amount of lignocellulosic materials, they are suitable for producing activated carbon while also reducing agricultural waste. Although commercial activated carbon is highly effective for adsorption, its relatively high production cost limits its large-scale application. At the same time, thousands of tons of rambutan seeds are discarded every year despite having the potential to be converted into valuable adsorbents. Therefore, this study aims to utilize this underused biomass to produce a sustainable and economical activated carbon. The significance of the study is that it is not only promotes waste valorization but also contributes to developing environmentally friendly adsorbents for pharmaceutical waste treatment. Additionally, this work provides adsorption data specifically for ibuprofen removal using zinc chloride activated rambutan seed carbon, which is still relatively underexplored. Previous studies have shown that pharmaceutical residues mainly enter water bodies through domestic sewage and hospital wastewater. Conventional wastewater treatment plants are unable to completely eliminate these contaminants. Alternative technologies such as membrane filtration or advanced oxidation process are effective but require high operational costs, experience membrane fouling, or may generate toxic byproducts. Therefore, adsorption has become one of the most attractive methods because it is simple, cost-effective, and can utilize renewable biomass materials to produce activated carbon. The adsorption behavior of ibuprofen is strongly influenced by its chemical properties. Ibuprofen is a weak organic acid with a pKa of approximately 4.9. Activated carbon removes ibuprofen through several mechanisms, including pore filling, hydrogen bonding, hydrophobic interaction, and pi-pi interaction between aromatic structures. Although may Although many agricultural wastes such as banana peels and walnut shells have been investigated, very limited studies have focused on zinc chloride activated rambutan seed for pharmaceutical removal. Therefore, this research attempts to fill that knowledge gap. The first objective was to prepare and characterize activated carbon derived from rambutan seeds. The seeds were chemically activated using zinc chloride at 2 to 1 impregnation ratio. After drying, the samples underwent carbonization in a tubular furnace at a 450 degrees Celsius under nitrogen gas to produce activated carbon. The samples were then washed using hydrochloric acid and distilled water until the neutral pH was achieved. Three characterizations were carried out, which is FTIR to identify surface functional groups, SEM to observe the surface morphology, and pH-PZC to analysis to determine the surface charge characteristic. This slide summarizes the activated carbon preparation process, where zinc chloride acts as a chemical activating agent by promoting dehydration and preventing structural collapse during carbonization. During pyrolysis, volatile compounds are removed, leaving behind a carbon-rich framework. Finally, washing removes residual zinc compound and open up pores, resulting in a highly porous activated carbon that is suitable for adsorption. The SEM image clearly demonstrates the effectiveness of the activation process. At lower magnification, the surface appears rough and fractured. At higher magnification, numerous honeycomb-like pores and cavities became visible. These well-developed pores significantly increase the availability of surface area, allowing more ibuprofen molecules to diffuse into the adsorbent. This indicates that zinc chloride activation successfully enhanced the porous structure. FTIR analysis identified several important function groups. A broad peak around 3,348 corresponds to hydroxyl groups. The peak approximately at 1,530 indicates aromatic carbon structures. Meanwhile, the peak around 1350 represent oxygen containing functional groups such as CO. These functional groups contribute to hydrogen bonding and other interactions with ibuprofen molecules during absorption. The pH-PZC value obtained was approximately 5.13. This represents the pH where the activated carbon surface has a neutral charge. Since ibuprofen has a pKa of approximately 4.9, operating near this pH minimizes electrostatic repulsion. Therefore, hydrophobic interaction and pi-pi interaction become the dominant adsorption mechanism, leading to a better adsorption performance. The second objective was to evaluate the adsorption performance of the prepared activated carbon. A UV-vis calibration curve was first established to determine unknown ibuprofen concentration. Batch adsorption experiments were then performed by varying these three parameters, which is contact type, adsorbent dosage, and initial ibuprofen concentration. Finally, adsorption capacity and removal efficiency were calculated to evaluate the performance. The calibration curve showed its excellent linearity with a high correlation coefficient, indicating that Beer-Lambert's law was obeyed within the selected concentration range. Therefore, this calibration curve could be reliably used to determine the remaining ibuprofen concentration after adsorption. The graph shows the effect of contact time on adsorption performance. Removal efficiency increased rapidly during the initial stage because many active adsorption sites were still available. As time progressed, the increasing becomes slower until equilibrium has reached. In the study, equilibrium occurred at approximately 60 minutes, after which only minimal improvement was observed. This indicates that most adsorption sites have already been occupied. Increasing the adsorbent dosage generally increases the removal efficiency. This is because a higher dosage provides more adsorption sites and greater surface area. However, after reaching the optimum dosage, the improvement became less significant because most of the ibuprofen molecules had been removed from the solution. The QE versus dosage shows the expected behavior where, as the adsorbent dosage increased, the less ibuprofen absorbed per gram because the same amount of ibuprofen is distributed over more adsorbent. This graph illustrates the effect of initial ibuprofen concentration. At lower concentration, higher removal efficiency was achieved because sufficient adsorption sites were available. As the initial concentration increased, the adsorption sites gradually became saturated, leading to a lower percentage removal. However, the adsorption capacity increased because more ibuprofen molecules were available to occupy the adsorption sites. The third observation was to analyze the adsorption equilibrium using different isotope models. There were two models that were evaluated, which is Langmuir and Friedrich. Langmuir assumes monolayer adsorption on a homogeneous surface. Friedrich assumes multilayer adsorption on a heterogeneous surface. The Langmuir model produced negative parameters, indicating that the assumption of homogeneous multi-layer adsorption were not suitable for my experimental data. Therefore, Langmuir was not an appropriate model for describing this adsorption system. In contrast, the Friedrich model produced the highest R-squared value of approximately 0.94, indicating a better fit. This suggests that adsorption occurred on a heterogeneous surface with multiple adsorption sites, which agrees with the porous structure observed from SEM analysis. I did not include the SIPS model that I wanted to do because the optimization coverage to a non-physical parameter value, which is n equals scarce, n equals 0, indicating that the model was unsuitable for describing the adsorption behavior of ibuprofen onto rambutan C activated carbon. In conclusion, activated carbon was successfully produced from rambutan seeds using zinc chloride activation. SCM and FTIR analysis confirmed the development of porous structures and functional groups suitable for adsorption. The activated carbon achieved a maximum ibuprofen removal efficiency of approximately 99.24%, demonstrating excellent adsorption performance. Based on the isotope analysis, the Friedrich model provided the best fit, indicating heterogeneous adsorption. For future work, adsorption experiments should perform in triplicate to improve statistical reliability. In addition, regeneration studies and real wastewater applications should be investigated too to evaluate the practical potential of this adsorbent. That is all from me. Thank you for listening.